Okay, looks like we're up and running. All right, so here's what we were talking about last time. You know what, before I get into the math, another quick reminder, don't forget about the attendance quiz there at the code. Check in, right? The quiz will disappear in like minute 45. So make sure to get that done quickly. Also, just a general reminder, make sure to have a system in place to make sure you remember, because I won't personally remember to remind you every time, of course. Hopefully it doesn't need to be said, but just in case, don't forget we have an exam in our next class meeting. I will be sending out some sort of an announcement, hopefully this afternoon, with a bunch of important things to know about taking tests in my classes. And it's just kind of procedural stuff, but it's all extremely important, and you're going to want to make sure that you read all of that. What I have done in the past is start the class meeting of the exam period with a discussion of these points, but these points keep getting more and more numerous, and it ends up pushing 10 minutes, and it's just not realistic anymore. So anyway, be on the lookout for that announcement. Okay. Alrighty. So back into the math. We were talking about directional derivatives, right, which we denote like so. And what is the point of a directional derivative? The big point, and I'm not going to repeat the whole speech that I gave on this last time, but the big idea is that partial derivatives are defined from the point of view of standard basis vectors, and in fact, every vector could be a standard basis vector, as long as you pick the right as long as you set up axes the right way in the first place. So really the idea of a partial derivative is much more general than we thought when we had this sort of very limited point of view of, coordinates being the boss, what's in charge. And they're not. Coordinates are a tool that work for us, and a limited tool, and we're not constrained by them. So generalizing as such, we get this idea of a directional derivative defined with that formula, computed with that formula, and interpreted as either one of those things, of course, or as the slope of a graph, or a multiplicative factor, or rate of change of a function with respect to distance traveled. Right? Which is a nice interpretation, sort of a natural, real-world sort of take on how to think about it. Okay. All right, and we did a couple of examples. All right, so picking up there, so I have to give you all a little bit of a warning here, and sorry to be the bearer of bad news again. Again, not my fault. I didn't do it. But the term directional derivative means different things to different people. And it's very frustrating. It's kind of like that thing with spherical coordinates, where, some people like to call the spherical coordinates by a certain naming convention, and others, in other contexts, use a completely different set of variables. We just have to deal with that. And likewise, you just have to deal with the following. Specifically, the unit vector requirement. A lot of people remove the unit vector requirement. Now let's think that through. Why did we have the unit vector requirement in here in the first place? And the idea was, I wanted to just make the case that, look, if you just turn your head to the side, you're not really changing anything, right? When you just do a rotation, distances don't change, angles don't change. Really not much of anything real actually changes. Just the coordinates that you write down, right? It's all basically the same. If you have a non-orthonormal axis system or basis that you write down to define your axis system, then all of a sudden that's not true anymore. Distances change, and things get a little weirder. A lot of people like to put in the orthonormality requirement for the axes, which effectively means that all the vectors have to be unit vectors. If you remove that, if we remove this unit vector requirement, you can still define something called a directional derivative You can still use this notation, and people do, so a heads up on that. They still mean this when they write that down. It is still computed by that. All of that works totally fine. The cost is that all this stuff down here is not true anymore. Right? So you got to give up all of that. So, okay, all right. So this seems like a bad deal, arguably. You know, you take away the unit vector requirement, and here, let me make a better color choice. We'll use the same color. Scratch off what we lose from scratching off that requirement. So why would anyone want to do this? And, well, two things. First of all, there are still a lot of vectors. Right? There are a lot of vectors that we might be interested in that might represent something natural, and we might want to talk about, for example, supposing that I'm at a point A and moving with velocity v, which is what this says, I might very reasonably want to know how fast is the function changing with respect to time. That's a very natural question. Very natural, very reasonable thing to want to ask. And it's super nice to know that you can compute that thing with this formula. This is a useful idea, right? So there's this trade-off, right? And this is true in a lot of situations in math, where the more that you assume, the more assumptions that you make on a theorem, the stronger of a result you can get. But the cost, the more assumptions you make, the more narrow the theorem actually applies, right? So the previous, the Math219, Colley's textbook, that notion of directional derivative, where we have the strong requirement that it be a unit vector, has more conclusions that you can draw, but it applies more narrowly only to unit vectors. And if you've got a non-unit vector, you've got to deal with that. Not that that's hard, but still, sometimes it's a little inconvenient. So be aware of both of these conventions. It's, again, unfortunate that the same term is used to describe, importantly, different things. How do we deal with that part of it? And the answer is that you just have to be on the lookout. All right? So, depending on who you're talking to, outside of Math219. Now, in Math219, we're going to stick with the book's definition. We're sticking with all of this in Math219 as written here in the notes, as written in the book. But outside of this course, be advised. Some people will use the word directional derivative to apply to non-unit vectors, and you cannot interpret that as a slope of a graph. It's not. And you cannot interpret that as rate of change with respect to distance, because it isn't. Right? So, heads up. All right. Okay, so moving along. Related idea. Doesn't look related, but it is. We're going to ask a question. The answer to this question is going to be interesting. We're going to start with a differentiable function. And we're going to assume that we're looking at a particular point A here in the domain. Here's the question I want to ask. Suppose I consider all possible directions from the point A. Right? There's a million different directions from A. I could talk about going that way or this way or that way or, take your pick. Of all of these possible unit vectors, constraining our attention to unit vectors because we want to focus on directions only. I'm just interested in I don't care how fast you're going to move. Maybe we don't even know yet how fast we're going to move. We want to talk just about the directions. Of those directions, which one will maximize the directional derivative? That's a pretty natural question, I think. So a silly example, let's suppose I'm out in the woods and I'm cold, right? And so there's me, I'm at the point A, and I'm cold, and I don't like being cold, and I want to get warmer, and so I want to know which direction should I walk or run to get warmer as fast as possible. Right? Which direction will make my rate of increase of temperature as great as possible? Because that's the direction I want to move. Now, whether I walk or run or how fast do I run, that's a separate matter. I can do that in any direction. But which direction specifically should I go? Does everybody see the question? Everybody see the naturality of this question? Everybody happy? Okay. All right. So, reasonable question. Now, I'm going to show you the answer in a second, but before we do, I want to talk about what we're going to call the answer to this question. And what we're going to call this depends on how you interpret the thing that we're maximizing. So, for example, let's suppose you interpret that directional derivative, as of course we can, as the rate of change with respect to distance. It's a natural way to interpret directional derivative. If I identify the direction that makes how fast the function is increasing as big as possible, I think we should call that the direction of fastest increase. I think that's a very reasonable interpretation. Whichever one of these ends up being, wrong color. Whichever one of these ends up being the answer, I would call the direction of fastest increase because it's maximizing how fast the function's increasing. So I think that language is extremely natural. It's very blunt, very obvious. Okay, but here's the thing. You might make a different interpretation. It's perfectly reasonable to interpret that directional derivative as being a slope. Now, detail, you can only interpret a directional derivative as a slope of a graph. Right? Again, you've got to be really careful about that. Only if you're looking at a graph. We've seen several examples of functions where you can't draw the graph. We don't have enough dimensions. Sometimes the graph is just not possible, right? But if you are in a situation where you can draw the graph, and therefore where you can interpret the thing we're trying to maximize as being a slope, the slope being the thing that tells you how steep the graph is, the thing that maximizes the slope, the thing that maximizes the steepness, the thing that maximizes how steeply you are climbing the hill as you go in that direction. I think direction of steepest descent. Pretty reasonable choice of terminology there. Right? So notice we do have here two different words. This thing, the answer to the question that we're trying to figure out. And again, I'll show you the answer in a moment. There are two pretty reasonable different terms based on different sort of interpretations of different ways of thinking about what it is that we're trying to figure out here. So heads up about these two terms. Now, for whatever it's worth, I will point out that no matter what function you're looking at, this always makes sense. Right? DFDS always makes sense. It doesn't rely on that you're looking at it from a certain point of view, that you're seeing the graph specifically. This is broad. It always works. It always makes sense. And so this term always makes sense. I prefer that term for this reason. Right? That said, this is the more common term. Direction of steepest descent is what you're going to see more commonly outside of my lectures and my notes. So heads up about that. Now, it might create some confusion for you. It certainly did for me. I was very confused trying to figure out how I was supposed to make sense of direction of steepest descent when I was dimensionally prevented from even visualizing the graph. You're not ascending anything if you're not looking at a graph. Right? So I used to find that really confusing. Anyway, heads up about that, and apologies for the, again, semantical confusion. Okay. All right. So I think we have that covered. Let's talk about how to actually answer the question. Again, we're trying to maximize the directional derivative. That's what we want to make as big as possible. Don't forget it's computed with a dot product. Don't forget dot products are computed with this formula. magnitude times the cosine of the angle. In particular, the gradient being one of the vectors, the candidate direction unit vector being the other vector. And because that's a unit vector, of course, this magnitude here is 1. So we'll just make that disappear. Factor of 1. You don't have to write down. So altogether then, here's what we're trying to maximize. Altogether, we're trying to make this expression as big as possible. How do we maximize that expression? Now, reminder, we're trying to maximize that expression for all possible directions by which I might start moving, but I have not actually started moving yet. Okay, so A is constant. We're not moving A yet. We're contemplating moving from A, but we have not actually started moving yet. So A is not changing. A is a constant, and that means that the gradient evaluated at A is a constant, and that means that this part of the thing we're trying to maximize is a constant. And so really, when you all said and done, this is all we need to maximize. Just need to maximize cosine theta. Nice and easy. How do you maximize cosine theta? Well, no problem. We maximize cosine theta by letting that theta equal to 0. Nice and simple. What happens when that angle theta is equal to 0? Keeping in mind that angle theta is the angle between the gradient and the v vector. Well, making that 0 would mean that the v vector would actually have to be the unit vector that's pointing in the same direction as the gradient. That's what it looks like when the angle between them is 0. And if it's the unit vector pointing in the same direction as the gradient, then it's the gradient divided by its own magnitude. So this is a lovely little argument, crisp answer to a natural question. I like the fact that this uses various interpretations and cool formulas that we know from the past. Really cool argument. And again, nice crisp answer to the question. Which direction should you go? Whatever direction the gradient's pointing, that's the direction you should go. Okay. All right, now natural next question. Okay. So we've agreed I'm going to go in the direction of the gradient. How fast is the function changing per unit distance as I move in that direction? I know the right direction, but I'm cold and I need some reassurance of, okay, yeah, but per mile that I walk in that direction, how much can I expect to warm up? Reasonable thing to want to know. And, well, that directional derivative computed with a dot product. Don't forget, we've already agreed that that direction is the direction of the gradient. And then, of course, this dot product is magnitude squared. And so I end up with magnitude squared divided by magnitude, which is just magnitude. So weirdly, the answer is again the gradient. Right? So let me summarize. What direction? Direction of the gradient. What's the punchline? Well, how fast is the function increasing? Magnitude of the gradient. Right? And I think this makes for a really nice summary and arguably a different take on what a gradient is. And let the record show, this is our first time of making any interpretation of the gradient as anything other than a notational convenience. Right? Up to now, it's just, well, we like to write it like this because it's a more compact formula. It's been nothing but a notational convenience until now. Right? But now we have natural geometric interpretation of it. The gradient is entirely characterized with geometry by its direction and its magnitude being what we just talked about. It's the unique vector that points in the direction of fastest increase and whose magnitude is the rate of change with respect to distance in that direction. Very crisp. So you could, depending on how you like to do things, you could take this as the definition of gradient and then kind of do a lot of the math that we've done so far in this class kind of backwards and derive from this the formula that we wrote down and used as our definition. Okay. All right. So it's a really nice way to think about the gradient. All right. Let's see an example of this in action. Let's see here. By the way, I can full screen. Oh, that's better. Okay. So we've got a hill. And the hill is in the shape of the graph. Notice that's a graph of this function given by that formula. And you can persuade yourself that the graph of that is sort of an upside down paraboloid like so. And by the way, make sure you can do that. It's a good little exercise. It's section 2.1 kind of stuff. Okay, and so now I am sitting on the hill right here. How am I going to describe where that is? Well, as most people do when you're trying to describe your location on the surface of the earth, you describe with map coordinates, right? If I wanted to, tell somebody where I am right now, I would say, well, longitude such and such, latitude such and such, boom, they know right where I am. I wouldn't bother telling them the altitude, right? I mean, it's probably understood that, yeah, I'm on the surface. I'm not 10,000 feet in the air, right? I'm not 700 feet underground in a mine of some sort, right? So it's very often, and I think reasonably, assumed that you're on the surface, of course. So notice the way I describe my location is just with the map coordinates. I'm just the point in the domain that corresponds to that point on the hill. And most of the time, by the way, we totally conflate these two things. So there's a little note down here. Let's see, I have to let's do it like that. A little note down here pointing out that most of the time, even though these two things are different, we will conflate them. For example, very often, not just me, this is very standard, very often you'll see a problem that says, so-and-so is at the point 1,3 on the hill. Okay, so technically the point on the hill is in 3 dimensions, 1,3 is in the domain of the function whose graph we're looking at. That's 2 dimensions. It's not the same. That's sloppy terminology. Very standard. Everybody does it. We're going to do it too. Heads up, be aware. And again, you have to be prepared to account for that in the math as a result. Okay. All right. So that noted. Question is, which direction is uphill? And by the way, how steep is it in that direction? So the answer is the gradient. All you got to do is take the function that we were given here and compute its gradient. And then which way is uphill? Well, whatever direction the gradient points, which is southwest. That's what direction uphill is. How steep is it there? Okay, well, the magnitude of the gradient. 2 square root of 2, which, by the way, is pretty steep, right? That's like 2.8 something. And if you think about it, a slope of 2.8 would be about like that. That's really very steep, right? How we doing? Everybody with me? You got to kind of look forward to these questions on an exam because all you got to do is compute one thing and you get to make 2 interpretations from the one computation. You just compute the gradient and then interpret what direction is it pointing and interpret what its magnitude is. Done. Yes? Sorry, I can't hear you.
How do we know if the function is increasing or decreasing? Because like if you take the vector that's like in the direction of the gradient, then it will be like changing one direction, increasing or decreasing. But like if you flip the gradient, it will be like opposite.
So I hear what you're saying. The gradient will always point in the direction the function is increasing. And so you can look at this calculation that we did to see that we computed what is the rate of change with respect to distance traveled in the direction that we just agreed upon, and it is positive, right? So it'll always point uphill, right? This isn't like a level set thing where, well, it's, the direction, it could be either direction. It's not like that, right? It literally always points in the uphill direction specifically. Yeah. Yes?
What if the increase in every single direction is the same?
Then the function is not differentiable. And none of this makes any sense at all, and there would be no gradient. So let's just consider a scenario. I mean, what would this hill look like where whichever direction you go is up, right? And I think you'd be at the bottom of a cone, right? You'd have to, there'd be some cone like this, and any direction you go, you're climbing out of the hopefully extinct volcano, right? So that's not differentiable, and none of this works. Is that satisfying? Yeah. Yes.
Did you say before that the length of the gradient is always constant?
Well, the gradient, what I should say is the gradient is independent of which unit vector you're contemplating, describing the direction that you're going to go, right? So if I'm standing here, and let's say the gradient is that way, and if I say, which direction should I go? I guess I could go that way, or I could go this way, I could go that way. As I contemplate different directions that I might go, the gradient's still that, right? So the gradient's independent of your choice of unit vector. Now, of course, it's going to change once you actually start moving. Once I say, I think I will go this way, and now as I go this way, I'm at a different point. I'm going to have a totally different gradient. As I climb a hill, it might get steeper, it might get less steep. Yeah. Okay, good. Good stuff. Anybody else? Okay. So, moving along, there's a neat relationship between level sets and directional derivatives and gradients. So now, very importantly, notice we have changed gears. Previously, we were looking at graphs, right? Now we're going to be looking at level sets. Totally different geometry. Totally different relationship between the function and the picture we draw. Totally different interpretations of derivatives. And we should expect totally different relationships between the pictures and the calculus. Okay. All right. So in this context, looking at level sets, by the way, here's a level set. Oh, you know what? Let me do that in green. Here's the level set. Specifically, the value of the function whose level set we're looking at is fixed at some value c on that surface. Okay. And let's consider what happens as I move parallel to the level set. Now, here's how you move parallel to the level set. I'm going to imagine, for example, that I'm on the level set. Now here I'm moving on the level set. I'm confined to the level set, and I keep moving on the level set. There's some curve there that describes my motion in the direction, in some direction on the level set. Now, very importantly, there is a moment when I'm at this point here. Let's talk about my velocity at that point. When I get to that point, my velocity is tangent to the curve, of course. But the curve is in the level set surface, which means that my velocity is also tangent to the surface. And here's the thing. I claim any vector tangent to the surface can be viewed like that. So there's another tangent vector. It's not the velocity of the path that I had previously drawn, but maybe it's the velocity of that path, right? And this tangent vector there, well, that's the velocity of that path, let's say. Any tangent vector is the velocity of some path that is entirely confined to the level set itself. And so let's ask the reasonable question then, okay, what is df ds for any of these tangent vectors? Well, any of these tangent vectors, they all represent motion inside of the level set. They represent motion on the surface where F is constant. F isn't allowed to change. You're on that level set, F is not allowed to change at all. F is just straight up C all the time. So if you're moving in such a way as to keep you on that level set, F isn't changing. Or said differently, its rate of change is 0. Now, okay, what do we conclude from this? Well, not anything immediately, just an innocent observation, so it would seem. Here's the interpretation. This is really nice, very powerful interpretation. Let's not forget what dfds is. dfds is the directional derivative. By the way, directional derivatives are computed with dot product with the gradient, like so. So if you know that these are all 0, that tells you these are all 0. These dot products. All these tangent vectors V. Dot product with the gradient is always 0. In other words, the gradient is orthogonal to all tangent vectors. Now let's draw a picture of what that could possibly look like. And here it is. We've got a bunch of tangent vectors here. All possible tangent vectors. If my gradient is orthogonal to all of those tangent vectors, now I'm going to make a geometric appeal here. I think this is pretty satisfying. If it's orthogonal to all tangent vectors, then it's got to be orthogonal to the surface itself. Right? And keeping in mind, if it's orthogonal to the surface itself, don't forget what the surface is. The surface is green again. The surface is a level set. So gradients are always orthogonal to level sets of that same function. And let's see here. I'll use the blue to represent the orthogonality. So that being a right angle is the orthogonality. So really neat fact, right? So now this is one of the big pieces of what I like to call the calculus of level sets. Remember, I know I say this a lot, but you got the calculus of graphs over here. This is various interpretations of algebraic objects of calculus in terms of what they look like on graphs. And then, wall, right? And then over here, completely different set of interpretations. If you're looking at level sets, totally different interpretations of calculus objects, right? And I think this is one of the big ones for the calculus of level sets. The gradient, clearly an object of calculus. It's a derivative of sorts. It's always orthogonal to the level set surface. And of course, orthogonality is a geometric interpretation. Okay, yeah?
So is a level set like any input leads to the same constant output?
Yep.
So I assume it would have been like a flat plane rather than something that's curved.
It depends on the function. So here, just as an example, let's consider the function x squared plus y squared plus z squared, namely distance from the origin squared. What happens when you hold that constant? Well, you get a sphere, and that's not flat. Right? So nonlinear functions will have non-flat level sets. Yeah, absolutely. Yeah. Okay. All right, really useful. Now I'm going to show you an application of this. I am going to leave most of this application for y'all to read. Again, you can see I've got this marked in advance for students to read. As always, please do make sure to read this. Please do make sure to think through all the little details. There's a lot of details involved. For example, notice in this example we're looking at, actually let me zoom in a touch. There we go. So we're looking at a graph of a function f. Right? And we've got that same little scenario where there's the point in the domain that describes what I'm putting into the function. And then there's this other point, not to be conflated, right? At least in terms of the algebra. I mean, again, casual lingo, we might conflate these, but the point that's sitting above that on the graph is not the same point. The input point is a two coordinate point in 2 dimensions. The point on the graph has 3 coordinates because it's on the graph. The graph lives in a different world. The graph does not live in the domain. Right? So, little details like this, you gotta think through and persuade yourself that this is the coordinates of that said purple point and that kind of stuff. So, the big idea though that I want to hit, to guide you in terms of thinking about how to do this is, this stuff down here. And remember, we've talked about this equivalence. Right? Seems like a silly thing to write down. I mean, the algebra on that is trivial, right? But notice this then allows us to take what came to us as a graph and to reinterpret it. You can see right there, equals a constant. We can therefore reinterpret this now as a level set. And of course, it's a level set of a different function, right? It's not a level set of f. It's a level set of this other thing. Z minus f that I'm going to call g. That's a function of 3 variables instead of 2. I mean, it's very importantly, different function, different domain, different formula. But I can take a question that came to me as a question about a graph. I have now reinterpreted it as a question about a level set, and now I can apply the calculus of level sets. And this ends up being super convenient. Let's think it through. We've got this surface is now a level set. What do we know about level sets? Well, as we just learned, gradients are perpendicular to level sets. And so check it out. I've got myself a normal vector for the tangent plane. Right, you pull this one little fast one where you rewrite a graph as a level set, interpret accordingly, identify correctly what the g function is, and boom, gradient of that new function is our normal vector for the tangent plane. So a lot of other little details. Make sure to read that, but that's the slick part. That's the tool for your toolbox. Is that idea right there? There's an example, and again, I think this is a pretty straight read. Make sure to read, think through the details, think through, again, all the little devils. Make sure you think all that through. Okay. All right. Next topic. So, I think a lot of y'all have seen in your calculus classes, this thing called implicit differentiation. Implicit differentiation gets treated very sloppily in most high school calculus classes. Even in a lot of college calculus classes. Not at Duke, right? I'm sure. But in a lot of high school calculus classes, certainly really sloppy treatment. And let me just for fun, let me go ahead and show you an example of this kind of sloppiness that I've seen students do a bunch, and I got taught this when I was in high school. Imagine you're looking at a circle. Let's say the unit circle, and let's suppose I want to know the slope of the tangent line to the circle at some point. All right, well, let's just take a derivative with respect to x, and you say 2x plus 2y dy dx equals the derivative of 1 is 0, and then off you go. And so dy dx, of course, we interpret as the slope of the tangent line. I claim that this little calculation here has committed a pretty serious crime. Pretty serious math crime. So here's the problem. We were given an algebraic relationship between x and y, and then, based only on that, I wrote down, as if it's legal, I wrote down the derivative of y with respect to x. Wait a minute, y wasn't given to be a function. I can't just assume that y is a function of x. And by the way, sometimes, even when you have a simple algebraic relationship like that, sometimes y really isn't. Truly is not. This is all garbage. Not a function of x. And if y is not a function of x, I don't even know what dy dx means. What is that? That's not a thing. You can't take the derivative of something that's not a function. Right? I mean, look back at your definition of derivative from Calc 1. Derivative is something you do to a function. You can't take the derivative of a bicycle, as I like to say. I mean, it's silly, right? So, okay, we've got a problem here. So how are we going to fix that? Now, let's see here. Let's look at this picture. Get rid of that. And again, keep in mind my interest is in, at some point on this curve, I want to know the slope of the tangent line. And at that point there, can I view y as being a function of x? Well, I mean, for this value of x, there are 3 different values of y. And so it's very tempting, and I think a healthy exercise to point out that for that value of x, no, this curve does not give y as a function of x. Right? And again, function is a very strictly defined thing. That's not it. Problem. Okay. All right. Well, here's the workaround. The workaround is to realize that if what you're actually interested in is the slope of the tangent line there, I don't actually need the whole curve to be able to describe the tangent line. It would be perfectly sufficient for my purposes to say, look, I'm only going to be interested in this part of the curve right there. Phooey on all of this. I don't care. It's got nothing to do with my tangent line. I'm just going to ignore all of that. I have no interest in it. I'm not even talking about all of that stuff. Let me talk just about that little blue piece of the curve. That little blue piece of the curve is plenty sufficient for me to talk about the tangent line. And of course, once I have a tangent line, I can talk about the slope. So we can get around that problem. So this is what we mean when we say locally. Right? I am not going to ask if y is fully a function of x. Locally means I'm going to restrict my attention to some small little neighborhood of whatever point I might be looking at, and then only in that little neighborhood, looking only at that little piece of the curve, now I want to talk about what's the tangent line, what's the slope, and that works just fine. Everybody good? At least at that point. And here's what we actually cannot work around. This is what we cannot deal with in any other way. Here's where we totally break down, and that is that at this point, even locally, it doesn't work. Because at that point, now you'll notice I picked exactly the point where the tangent line is vertical. Even locally, that little piece of blue curve right there, why, it's still not a function of x. And it doesn't matter how small you make your little yellow neighborhood, no matter how myopically you restrict your attention, no matter how locally you mean, it's still got this problem that it kind of wraps under itself. You lose. Y is not a function of x. It is not, very importantly, not that dy dx is undefined there. Let me bring it back. It is not that dy dx is infinity. It's not. It's not that dy dx is undefined at that point. Not really. It's that the word dy dx, the phrase dy dx, doesn't even mean anything in the first place. It's not that there's not an answer to the question. It's that there is no question. Everybody see what I mean? You can't take a derivative of something that's not a function. Alright, so, alrighty. That's what we need to worry about. right? This is the problem that we want to make sure that we avoid so that I can do Calc 1 style implicit differentiation. And let's see here. It looks like we're about out of time. So with that said, we'll draw the line. Oh, wait a second. No, why do I keep doing that? I keep thinking 11:05 is our, okay, sorry. We've got 5 minutes left. Sorry. Here we go. Continuing. You don't have to read this part, but I'm going to hit the highlights again. I think this is really good intuition for how to deal with this question. And it goes like this. This is the kind of problem that we're interested in. It's where the curve wraps under itself. The whole point to that being a problem is because it's got a vertical tangent line. The fact that it has a vertical notice I didn't say derivative. The fact that it has a vertical tangent line is what makes it possible for the function to wrap under itself. Vertical tangent line means that we have a horizontal gradient after all. Don't forget, gradients are always orthogonal to level sets. We are looking here at a level set of some function f. And don't forget what gradients are. Oh, whoops, wrong color. Gradients are partial of f with respect to x, partial of f with respect to y, and that being horizontal means that its second coordinate is 0. So this is the big point, and now let me just summarize. Problem means the y partial is 0. And now I remind you of this lovely construction, little logical construction called the contrapositive. P implies Q, has contrapositive, not Q implies not P. Said differently, if the y partial is not 0, right? If that doesn't happen, well then there's no way that that could happen either. And so no problem. So that's our test. Look at the y partial of f. Make sure it's not 0. If so, you're good. Go ahead, implicit differentiate all you like. Okay, so this is called the implicit function theorem. Here's the three-dimensional version of it. Now we enter into an area where you've almost certainly not seen this in a Calc 1 class. There's 3 variables now. But if you have a level set, let's see here, back to highlighters. If you have a level set of a function of 3 variables, then you've got some surface, maybe like that. Locally, can I view z as a function of x and y? Well, it depends on where you are. If you're at a point like this, yeah, sure. If you're at a point like that, you just restrict your attention sort of locally like that, and yeah, sure, z is a function of x and y. Vertical line test passes, no problem. Unless you're at a point like this. If you're at a point where the surface actually kind of wraps under itself, aka if there is a vertical tangent plane. If there's a vertical tangent plane, well, that would mean that your gradient is horizontal, and of course that would mean that the z partial would be 0. So you see we have an analogous sort of situation. Instead of the y partial being 0, now it's the z partial that would have to be 0. And again, you can turn this around and describe the contrapositive. Okay, what's always the answer? No matter how many variables you have. By the way, we've drawn pictures in 2 and 3 dimensions, and they get harder to draw the higher the dimension goes, and at some point you can't even draw them. But what always works is whichever variable you would like to know if it is or is not a function, take the partial with respect to that variable. We want to know if y is a function, take the partial with respect to y. If you want to know if z is a function, take the partial with respect to z. Nice, crisp little pattern always taking the partial with respect to whichever variable you would like to view as a function. So in this, if we want to view xi as being a function, you take the partial with respect to xi. And non-zero, no problem. So this is called the implicit function theorem. We'll end it there and see some examples next time. I think we're out of time now. See y'all later. Have a good rest of your Wednesday.